So in the previous video, we got a conceptual idea of how to measure the circulation of a vector field. And we had this pedal wheel that we used to help us get an idea of how big this circulation, this rotation in a vector field was. But we can't carry around a little pedal wheel and stick it into a vector field and watch it rotate and to figure out how much circulation there is in a vector field. And so we are going to use some mathematical ideas to help us measure these quantities. And so imagine taking this pedal wheel, and I'm going to draw the handle of this pedal wheel and replace it just with a vector. And I'm going to take a normal vector n. And I still have p at one end of this vector. And then instead of drawing in my pedals, I'm going to connect the tips of my pedals and draw just the circle that I get if I do that. So imagine the pedals are inside here, but I don't draw them, I just draw a circle around them. This gives me a curve C, and the direction of that curve C is determined by the right hand rule. So imagine your thumb is going in the direction is pointing up in the direction of your vector, and then your fingers are curling around the curve, and so that gives you the direction of the curve C. So this is the stylized idea of my pedal wheel, just with a vector and a curve. And then inside the curve, you can imagine there's an area right here. There's an area inside. Now, of course, I can point my vector n in one direction, or I can point it in the opposite direction. If I point it in the opposite direction, I'm going to try to draw it just parallel, same length, n. Then with the right hand rule, if I draw my curve n, it would go in the other direction. I have the opposite direction right here. And I again have an inside right there. And our vector n, imagine, is the handle of the pedal wheel. And so with this abstraction of the situation, we can imagine that to compute how fast my stylized pedal wheel is rotating is given by a line integral. The line integral around the curve C of my vector field. So that is the first thing we want to note down. So I have a couple of comments right here. So comment number 1, the line integral around C of f dr gives computationally the circulation of f around the vector n. So there we go. Now, the next step that I want you to consider is, imagine the pedal wheel has long pedals or short pedals. That will influence how big my curve C is, and that may influence how big this line integral is. But if I want to know how much rotation is there in a vector field, this is I want to know what is happening at a point. So really the idea that we are after is more of a circulation density. We would like to know what is happening at a point in the vector field. And so that's our next definition right here. So we would like to define the idea of circulation density of a smooth vector field f at a point xyz around the direction of a unit vector n. And to define that, we are taking the circulation that we just said we can measure with a line integral, but we are going to divide by the area inside of the circle that the line integral is around. Because we don't want the size of C to influence this idea of circulation density. And so we are dividing by this area, and then imagine you're taking smaller and smaller circles. So you're letting the area go to 0. that gives us this idea of a circulation density that doesn't depend on the size of this circle that is in the line integral. And so our second comment then is that this quantity, the circulation density, which is denoted by circ sub n of our vector field f at a point xyz, this quantity measures the circulation per unit area around our normal vector n. So the quantity circ sub n of f, so circulation density, measures the circulation per unit area around n. And so, I mean, that's the same as with density, the way that you've seen it before. You have mass per unit volume or mass per unit area or something like that. So it's per unit something. And so in this case, it's the circulation per unit area.